Good afternoon everyone. Today I am going to discuss few examples on the topic relations. In the last class I have discussed about the types of relations. So today I am going to explain these types of relations with the help of example. First example, number 1. So we let n be the set of natural numbers and R be a relation defined on n by number 1 R equal to x comma y such that x comma y belongs to n, x plus y equal to 10. And number 2, R equal to x comma y such that x comma y belongs to n, x plus 4y equal to 10. So determine whether each of the above relation is reflexive, symmetric and transitive. So we are going to discuss about this question. Let n be the set of natural numbers and R be a relation defined on n by R equal to x comma y such that x comma y belongs to n and x plus y equal to 10 and R equal to x comma y such that x comma y belongs to n comma x plus 4y equal to 10. So determine whether each of the above relation is reflexive, symmetric and transitive. So I am going to solve this one and this will be the homework. So solution, n equal to set of natural numbers and R is defined as x comma y such that, or that x comma y such that x comma y belongs to n, x plus y equal to 10. So first we have to list all the elements. Here. So first we have to choose x, then accordingly we have to choose y. So if we choose 1 for x, then we must have 9 for y. So 1 comma 9, that will give us 10. Similarly we have the other pairs, 2, 8, then 3, 7, then 4, 6, then 5, 5, then 6, 4, comma 7, 3, comma 8, 2, comma and 9, 1. These are the elements belongs to the set. Now we discuss about the reflexivity, symmetricity and transitivity one by one. Reflexive condition. Clearly 1 comma 1 does not belongs to R. So the element 1 comma 1 is not belongs to R, 2 comma 2 not belongs to R. So that's why it is not reflexive. R is not reflexive. Okay, R is not reflexive because 1 comma 1, 2 comma 2, 3 comma 3 etc. are not belongs to. Next we are going to discuss about symmetry. So symmetry. So we let x comma y belongs to n such that x comma y belongs to R. We consider x comma y belongs to N such that x comma y belongs to R. That is, ordered pair belongs to R. That means x plus y equal to 10. If x plus y equal to 10, this is same as y plus x is also equal to 10. Same condition. So from here we can write y comma x belongs to R. So as we see that x comma y belongs to R, we are also able to find that y comma x belongs to R. So that's why we can conclude that R is symmetric. R is symmetric. Okay, R is symmetric. So next we are going to discuss about transitive. So transitivity condition. We observe that what? Okay, this two part 2, 8 belongs to R and 8, 2 also belongs to R. 2, 8 belongs to R, 8, 2 belongs to R, but 2, 2 not belongs to R. If 2 is related to 8, 8 is related to 2, then 2 must be related to 2 for transitivity condition. But here we see that 2, 2 does not belong to R because 2, 2 is not equal to 10. Therefore, R is not transitive. R is not transitive. So we have discussed about all the conditions: reflexivity, symmetricity, and transitivity in this example. So let us take one more example. Example number 2. We will let R be the set of real numbers and we define a relation R on real number R by R equal to A comma B such that A is less than equal to B. Say whether the relation R is reflexive, symmetric, and transitive. So let R be the set of real numbers and we define a relation R on the real number by this relation A comma B such that A is less than equal to BQ. Check whether the relation R is reflexive, symmetric, and transitive. So we are going to discuss about all these three conditions. So sometimes it is not possible to prove by the theoretical method, then we need to introduce a counter example. Then we can come into the conclusion. So we are going to solve this problem step by step. So solution: R is set of real numbers. And here the definition for the relation is A comma B such that A is less than equal to BQ. Now first condition is reflexive. So we let A equal to 1 by 2, which is a real number. Clearly 1 by 2 is a real number. We observe that 1 by 2 is not less than equal to 1 by 2 whole cube, because 1 by 2 is equal to 0.5 and 1 by 8 equal to 0.125. So 1 by 2 is not less than equal to 1 by 2 whole cube. Therefore we can conclude that 1 by 2 comma 1 by 2 is not belongs to R. So therefore R is not reflexive. Here we see that R is not reflexive. We have one example, A equal to 1 by 2, and we observe that 1 by 2 is less than equal to 1 by 2 whole cube or not. If it is not, then 1 by 2 comma 1 by 2 does not belongs to R. Hence we say that, hence we can conclude that R is not reflexive. Now symmetry. Symmetry. Okay, we let A equal to 1, B equal to 2, both are real numbers. We observe that 1 is less than equal to 2 cube. Therefore 1 is less than equal to 2 cube means 1 is less than equal to 8. 1 is less than 8, so condition is satisfied. So 1 comma 2 belongs to relation. But 2 is not less than equal to 1 cube. 2 cannot be less than equal to 1. So therefore 2 comma 1 does not belongs to 2 comma 1 does not belongs to R. We see that 1 comma 2 belongs to R, but 2 comma 1 does not belongs to R. So the condition for the symmetric is not satisfied. Therefore R is not symmetric. R is not symmetric. So next is transitive. So transitive condition. Transitive condition. We take example here. 12, B equal to 3, and C equal to 2 belongs to R. You can take any numbers by yourself, but the care should be taken that all the conditions, first two conditions must be satisfied. So here we observe that 12 is less than equal to 3 cube. Yes, 12 is less than equal to 27. This implies, so 12 comma 3 belongs to, and 3 is less than equal to 2 cube. Yes, 3 is less than 8. So that's why you can say that 3 comma 2 belongs to R. But 12 is not less than equal to 2 cube. 12 is not less than equal to 2 cube. That is 12 is not less than equal to 8. So if 12 is related to 3, 3 is related to 2, then we must have 12 related to 2 for transitive condition. But it is here, it is not satisfied. Therefore R is not transitive. R is not transitive. Here R is not transitive. So this is the second example. So now I am going to explain another example. Explain another example. So example number 3, we will let I be the set of all integers, m be a positive integer and R be a relation defined on I by R equal to x comma y such that x comma y belongs to I, comma x minus y is divisible by m. Prove that R is an equivalence relation. R is an equivalence relation. So we let I be the set of all integers, m be a positive integer, and r be a relation defined on I by r equal to x comma y, such that x comma y are integers and x minus y is divisible by m. We need to prove that r is an equivalence relation. So proof will be like this. So solution, here I equal to set of all integers and r is defined as x comma y such that x comma y belongs to I, x minus y is divisible by m. So first condition we are going to say reflexive. So we can take any element, we can take any integer, a belongs to I. Then a minus a is equal to 0. Yes. A number, if we take any number and subtract it from itself, then it is equal to 0, which is divisible by m, because 0 is divisible by every non-zero number. So therefore we can say that a comma a belongs to R for every a belongs to I. Therefore R is reflexive. So first condition is satisfied. R is reflexive. So we need to check the other two conditions are satisfied or not. If satisfied, then it is an equivalence relation. So next condition will be symmetry. So here we can take, we let a comma b belongs to I such that a comma b belongs to R. A comma b belongs to R. Therefore a minus b is divisible by m. So as it is divisible by m, so we can write a minus b is equal to m a for some integer a. So we can write b minus a is equal to m into minus k. This shows that b minus a is divisible by m, and this is also shows that s belongs to R. Here we take a minus b is divisible by m, as it is a comma b belongs to R. So a minus b will be equal to mk, because as a minus b divided by m, so we get some integer k here. So a minus b is equal to mk for some integer k. So if we multiply both sides by minus 1 or minus sign, then we get b minus a equal to m into minus k. So this shows that actually b minus a is divisible by m. As b minus a is divisible by m, so b comma a belongs to R. So a comma b belongs to R and b minus a also belongs to R. So from here we can conclude that therefore R is symmetric. R is symmetric. So we are going to discuss the next condition, that is transitive. So transitive. So we let a comma b comma c belongs to I, such that a comma b belongs to R and b comma c belongs to R. This gives us a minus b is divisible by m and b minus c is divisible by M. We observe that here A comma B belongs to R, so A minus B is divisible by M, and B minus C is also divisible by M. So we can write here A minus B is equal to M K1 and B minus C equal to M K2, where K1 comma K2 are some integers. Now A minus C equal to A minus B plus B minus C. This implies MK1 plus MK2. So after getting this one, we can write A minus C is equal to A minus B plus B minus C. So MK1 plus MK2. MK1 plus MK2. MK1 plus MK2. This implies K1 plus K2 is M. So we can easily conclude that A minus C is divisible by M. Therefore, A minus C belongs to R. So we see that first A comma B belongs to R, then A comma B belongs to R, and B comma C also belongs to R. By supposing this, we are able to show that A comma C belongs to R. Therefore, R is transitive. As all the three conditions, reflexivity, symmetricity and transitivity are satisfied, so we can conclude that R is an equivalence relation. R is an equivalence relation. So in the next class, I will explain few more examples on this topic. So keep watching, subscribe, like and share. Thank you.